Good morning, everyone. Where did we stop last time? We actually stopped with first order systems. We talked a little bit about control inputs, right? Because our systems are linear, we can actually restrict ourselves to very simple inputs like an impulse, a step, or a ramp. Because all the other things, we can basically think of a decomposition of these complicated signals in these basic signals. So bottom line, we can stick to simple signals. Okay, as an input. Then we discussed about proportional systems. We basically discussed that there are systems we can classify in different classes. Mainly how the input is propagated to the output, can be integrating, can be differentiating, can be proportional. And we soon will have some exercises on that. So really try to think on a little bit mathematical, right? So what happens if I integrating something constant? What happens if I differentiating something constant? What happens if I take something constant and multiply it with a factor, with a proportional gain, right? So this is the key here. Then we said, okay, proportional system is just a gain, it's actually not system, it's just a factor. Then we went to the proportional system with a first order lag, and I tried to explain to you where this lag comes from, right? So we have an additional contribution by the derivatives of our output signal, right? And today I want to summarize this proportional system with the first order lag. We're going to do solving the ODE so that you see once in this lecture where this whole solution comes from, and then we're going to move over to the proportional system with a second order lag. Okay. Okay, so let's jump in. You see Professor Westenthaler in the back. He's for lunch. No problem there. So yeah, our office is actually pretty busy. That's why we sometimes have some 1 or 2 minutes delay when we start lectures. So yeah, that's our little issue here. But we will manage that as usual. Okay, so proportional system with the first order lag. I'm basically try to recap. If you have any questions, don't hesitate to shoot them into our chat here. Okay, first order system. We said has this ODE, right? So it has basically this guy here, this first part. This is the proportional system, right? Because our input is transferred proportionally to the output. We will see next time what it means when we have an integrating or differentiating system. Then we have either u dot or integral u here. But this time we're sticking to the proportional. So we take our input and multiply it with something with constant. And on the other side, we have the output. This is the thing we are interested in. Think of the car. Our input could be the steering angle, and our output is the position of the car on the road. Okay, so if we have a proportional system with a first order lag, we have this guy additionally here. And I tried to explain to you why is this guy actually introducing a lag to our output. Why? Well, if you bring that to the other side, you see that there's a minus there, right? So it depends on how big this t is, but it makes our system a little bit slower, right? And this is what you see here. You need some time to react, to move from one point, from one equilibrium to the other. And for those of you who have actually started with the practical exercises with this espresso machine, realized that you can interpret a PT1 system or any stable proportional system moving from one equilibrium, so from one Gleichgewichtszustand to another, zum anderen Gleichgewichtszustand, in a lagged fashion. Think of when you're sitting at home in your room and it's winter and it's cold outside, it has 15 degrees in your room. That's an equilibrium, 15 degrees, right? It's not changing at all if, for example, you don't change the heater and the outside temperature is not changing. So it remains at 15 degrees. So then, okay, it's a little bit cold. I'm going to turn up my heater. Okay, what happens is it's not going to be immediately 25 degrees, right? Kind of natural. It takes some time. And it's this process can be approximated very well with a first order system. So you wait half an hour or an hour and it will reach 25 degrees, right? So you're moving from 15 degrees or 17 degrees to 25 degrees, from one equilibrium to another. So why is the temperature not always increasing? Well, you are losing energy to the outside because it's cold outside, right? So it's a proportional system. If the temperature would increase until you get melted, right? That would be an integrating system, right? We don't have that effect. Integrating system could be your bathtub. If you turn on the water, the altitude is always increasing until it spills over. That's integrating. We are dealing with proportional system, and I think a nice bridge in your head is to think of a proportional system moving from one equilibrium to another. In a lecture, I'm starting from 0, right? But that doesn't mean this has to be always the case. It's just for simplicity here. We're starting from 0, and in this case, we're going to 3. In the lab exercise, you're actually starting with the room temperature because you're assuming your espresso machine, the water, what you want to heat up to 96 degrees, already has 20 degrees, right? You're not starting from 0. That's not your equilibrium. When you have your espresso machine at home, the water will somehow have the room temperature. So this is your equilibrium. So be careful. The ODE description, this guy always gives you like delta values, right? So you need to take into account any equilibrium. Of course, in the lecture, I'm showing you the easy part that we start from 0. But you could start from 20 and go to 125. The delta is going to be 105. And this is what this, how do you calculate your gain in there? Okay? Okay. So that's the recap from last time. Now I want to actually do 2 more examples here of a first order system, and I try to connect to you and show you that all these systems, no matter if they're from electric engineering, from mechanics, or from I think it's a thermodynamics problem, which is coming next. Actually, I don't remember. Okay, open loop control problem, hydraulic problem, actually look pretty much the same. Okay, so take a look at this electronic circle here, right? You know by Kirchhoff's voltage law that all the voltages in there need to sum up. So you have some input voltage U, you have a voltage at the resistor and a voltage at the capacitor. So I looked it actually up, and condensator is not the right translation for condensator, it's capacitor. So I was wrong last time. So I fixed that yesterday. Okay, so this is kind of basic electronics law, right? So what we also know is, sorry, that the capacitor, we can express the voltage by the integral of our current and 1 over the capacity. So if we take this guy and build the derivative and multiply by C, this is the result, right? It's just rewriting this equation. Okay, so what we can do next, what we are ultimately interested in, we give here some input voltage U, and we are interested because this is a measurement unit, right? A Messgerät. What we want to know is the voltage on our capacitor. So this is going to be our output. And we want to have something like Y of U in ODE, right? So how is our output depending on our input? Okay. So what's next? Okay, we can take this, we know that in the whole circle, the current is constant, right? And we also know that there's this law that the voltage is equal to our resistance in the resistor times our I. So that's why we can actually say our resistor voltage is equal I, and we can plug in I U dot C times C times R, right? Yes. And if we plug that in, we finally come to that differential equation. And now you should see that this is basically exactly the differential equation. We said this is the output voltage, right? So this is basically our U dot plus U is equal, and we define our the input voltage as our This is our output, what we are interested in. So we named it Y, and this here is the input voltage, which is here. So we simply write U. And now you see what's the first order system behavior. Well, we can say our time constant is resistance time capacitor, and our gain here is equal, well, it's easy, 1. So what does it mean? Well, that means when we apply an input voltage, it's transferred exactly the same to the output voltage, because this guy here is 1, but only in steady state. There is a transfer behavior, like a PT1, like this here. It takes some time, and this time depends obviously on the resistance and on the capacity of the condensator, and this totally makes sense, right? So if I increase the resistance in my resistor, if I take a different resistor with a bigger resistance, it will take longer that the output voltage will be equal the same as the input voltage. Same goes for the capacity. If the capacitor is pretty big, right, so it can take a lot of voltage in. So it will take a lot of time that the output voltage reaches the input voltage and reaches this other equilibrium. So this is the interpretation of the time constant. I know not everyone is a big fan of electronic circuits. That's why a little bit a different example where we have a volume, right? So it's a hydraulic example. You have a volume there, and you have some pressure. So this PE is your input pressure. Let's write it. Input pressure. So we define U equal PE. So I said to you, I always like to use the variable U for the input, and our output is going to be the pressure in the volume. And we name that Y. So our Y is equal to this output pressure, right? Okay. So what do we know? And we have a throttle here. So we have a Drossel here. And obviously it's kind of a resistance. Similar we have in the electric example, right? So we can set the resistance. Okay. So we get a flow rate depending on this resistance and depending on the pressure difference, right? So our flow rate, so how much molecules are moving in here, depends obviously on the resistance and on the pressure difference. So if PE, our input pressure, is larger than the output pressure, in the pressure in our volume, the molecules going to move in here, right? So if we increase the resistance, they're going to move slower. Okay, so that's the flow rate interpretation here. Okay, so now let's think about how is the pressure changing in here. Well, the pressure here is changing, so PA dPA after dt. Well, this is changing depending on the flow rate, right? So if we have a big flow rate, the pressure is increasing, but obviously also the volume plays a role here. So we need to divide 1 over the volume. If the volume is big, for the same flow rate, the pressure change is going to be slower, right? Okay, so now we're simply going to take this Q here and plug it into this equation, and you again see that you come up with this first order system. And now we're going to take our definitions of our input and the output, and we can rewrite this is going to be our output pressure derivative plus Y is equal U, and there's a 1 there, and we have a time constant, and the time constant again is R times V. So again, this time constant describes the time how fast or how slow we're gonna move the pressure. So if this is PA, right, and this at the time t0 we have a certain pressure, and to change the color probably. And now we apply an input pressure, and this time constant gives us how fast we're going to move to this output pressure. And here, PA equals PU, right? or y equals u. In steady state, they're going to be the same, but we will need some time. And how long this time is depends on this time constant. And again, this totally makes sense, right? The interpretation of this time constant. If we take a bigger volume at the end, it takes longer. So our time constant is going to be increasing. If we turn down the throttle, so we make the molecules move slower through there, then it will take longer that the whole volume fills up. And this is why the time constant is directly proportional to our resistance, our throttle basically, and the volume itself. Okay. Obviously, you will find a lot of PT1 systems, especially in thermodynamics, electrical engineering, and so on. Next, I want to talk with you. Actually, these are all PT1 systems, right? First order or the ODEs with lag. So how do we actually solve them? And here, we all learned in our math lecture that we can solve this thing on paper. And actually, a PT1 system is pretty straightforward, right? However, in practice, we will never solve that on paper anymore. For those who started with the lab exercise, there are PT1 systems in there, right? And you did not solve that on paper. You just pressed play, right? So pressing play in Simulink means that you're actually initiating a numerical solver, right? So what happens is that this ODE is solved stepwise for a given input, right? So it's basically converging to a solution. You can have methods to solve that numerically. If you do it on paper, as you learned in math, you're doing analytically. You're actually solving this. And for only once, we will do that analytical solving now because it's important to understand where this transfer behavior is coming from, right? And this sets the basis for all the other ODEs, which gonna be a little bit more complex, right? PT2 systems, PT3, IT1 system, integrating system. The idea is always the same. You take your mathematical formula, you look in, and then you figure out a way how to solve this ODE analytically. In practice, when you work, you will simply code it up and let the numerical solvers do the job. They are much faster because we will probably will need 20 minutes. MATLAB needs less than a second. But still, for the understanding, it's important where the solution is coming from, right? So what do we have? We have an ODE. It's our system, right? It describes, for example, this electric circuit. We have an input, in this case, the voltage, and we want to know the output. And here's the thing, the input for now can be anything, right? The input, this input voltage could be a step, could be a ramp, and so on. But we will see how, where we need to set this input that we actually can solve this guy. Okay, long talk. I will show you the solutions. You should have learned that in your math lecture. So again, that's what I said. A PT1 can be interpreted pretty nicely as a lag transition from one equilibrium to another. So what happens if you solve these guys? Okay, solving a first order ODE, you can look at your mathematical formula. You first go for the homogeneous solution. So here really the intention is more that you understand what the homogeneous solution is than that you actually are able to solve it. The homogeneous solution is you set your input to 0, right? This is when you solve this ODE, and why I'm so keen about that you understand it, because this is the basic idea, and we're going to tackle it in 1 or 2 weeks, about stability, right? The stability of your system is not depending on your input, right? And I think the key or the fundamental of this understanding is laid at this position here in the lecture, right? A system is stable if it remains in its equilibrium. Remember the stick, my famous stick where I just got sushi sticks here now? This would be an unstable system. I'm not doing anything, I'm just let it go. This would be a stable system. So I'm not giving any input, it's just remaining. It's if I do an input, it's going back somehow to that position. So this is what we call a stable. So and to figure out if a system is stable or not, you only need the homogeneous solution. You don't care about the input, right? Obviously, if you have a car is a stable system. If you push your car, it will run and it will stand still at some point. So it's not going to drive on its own, hopefully. However, you can sit in and give an input to that system and drive it against the wall, right? So then it's broken. You shouldn't do that, but then it's broken. But this has nothing to do with stability. You can always apply an input that you crash your system, right? If the system is stable or not, it's really only the eigendynamics without input. And this is actually a homogeneous solution. And why is this the homogeneous solution? We will learn about that. Okay, so you solve for the homogeneous solution. This is the first part. And then you solve for the particulate solution and the second part. And this particulate solution now really depends on your input, right? And the overall solution, so this y of t, this is what you're interested in, right? So you want to know where your car is moving at. You want to know what how the output voltage looks like. This is just a composition and actually the addition of this homogeneous solution and the particulate. You just add this together. Obviously, you have this integration constant. You need to evaluate the initial condition and so on. And then you will have your answer. And this guy here, this is the answer of your system, right? And this is basically Kp minus this exponential function. And this negative exponential function is exactly what you see here, right? So it's a decaying function, but it's negative. So it's basically subtracted from our Kp times our input. Okay, so I know this is pretty compact. That's why I actually want to do this step-by-step solving of the ODE slowly. Okay, so I've written it down. So we assume we have a PT1 system, right? And we know now that a PT1 system looks like this. There's a time constant. It has the first derivative. This makes it a first order, right? So if you have a second derivative, it's second order. Y of t, and we have our famous proportional gain here, u of t. So, okay, and now as an engineer, you want to know how y of t looks like for a given input, right? So here, your input can be arbitrary, but if you want to solve that, okay, there's a question why we are only looking at step functions as inputs. Well, this is what I tried to convey you last time, right? Step function is a fundamental function, and as our system is linear, you can think of any crazy input you like, right? But you can take this input and decompose it in simpler inputs like steps and impulses, right? And because the system is linear, you can add all these things together. So you can take your crazy input, decompose it, and compute it only for one step there. And then you know your output's going to be composed of all of these things. Because it's linear, you're allowed to do this. And this is why in control engineering we say, okay, the step input and the impulse input provides us enough information to learn about the system, then or to understand the system, to know what's happening and what the ultimate goal is. You want to understand your system to design a controller, right? Obviously, if you say, okay, this is not realistic, in practice, I definitely gonna have a ramp input or a sine input, then you should look at also at these inputs. But you know you can take a step back and only learn about these basic inputs first, because if your system, let's talk about stability, if your system is going to be unstable, you're going to excite it with a step and you will see it's going to be unstable. But it's unstable per se. It's going to be unstable for every other input. So you don't need to think about any other input than these very simple ones, right? It's actually, a simplification we're going to take. If you do aircraft control, for example, you're always going to take a look, okay, how is my aircraft reacting to when I design a controller to a step, when the controller does a step input. Obviously, then you say, okay, it looks good, but that might not be realistic. It's going to be a slow input, so it's going to be looking like an input like a PD1, for example. Then you can take a look at this also, but it's not going to change dramatically. All what you need to know is the time constants and the proportional gains, because your system is described by the time constant and this proportional gain. These parameters do not change when you change the input. So you're more interested about the characteristics of your system than a specific input, right? As I said, obviously, if the step response looks like fine, you can always find an input to crash your system, but that doesn't matter. You trust your pilot that it will not crash the system, right? I hope that kind of clears that up, why we're looking at only these simplistic inputs. Okay, and again, we're gonna assume we're gonna apply an input which is the unit step function, right? So it really looks like 1 here. It's going to move up, and then it's going to be for t equals 0 over t. Okay, so again, why? Now you could say y equal 1, why not equal 3? Because it doesn't matter, right? Because the system is linear. If you solve it for 1, you get your answer. And if you want to solve it for 3, then just multiply this answer by 3. So you make your life easier by solving it for 1. Obviously, in the lab exercise, I don't let it solve for 1 just to get a little bit more intuition. But the system, as it is linear, you can just take the output and multiply it with this factor. Okay, so, and now we know that what we are ultimately interested in is this y of t. Okay, and for that we need to, so we know that this y of t is composed of the homogeneous solution plus some particulate solution. And I'm going to write off t, although this here it's not a function of t. Okay, and the homogeneous solution assumes we're setting our input to 0. So this is our eigenmotion, and it's really called eigenmotion. So it's in English, it's taking the German word here, right? Eigenbewegung. We don't care about the input. And here, the particulate solution depends on the input. So I guess some of you might think this is what you have learned already, so it's a little bit boring, but I usually do the solving once in the lecture, just that everybody is on the same page. Okay, and how do we solve that? Well, we first solve for the homogeneous solution, then the particulate. Okay, let's start with the homogeneous solution, right? I'm going to do the abbreviation, just writing YH and not always homogeneous. Okay, so we set u of t equal 0. Okay, that's easy. Let's write the equation down. Y dot of t plus y of t is equal 0. Okay, so then we know that this is nothing but dy after dt is equal minus y. I'm omitting now the function of t because it's getting a mess otherwise. Okay, so if we do a little bit of rewriting, we will get, let me think, 1 over dt is equal minus 1 over t times y over dy, right? So I basically multiplied by dy. Now there's somewhere an error there. That is when you do it too fast, right? You divide it by d. No, it's okay. So you divide basically by 1 over dy and 1 over t. Yeah, that's it. Okay, now we're going to take the inverse of it. We get dt is equal minus t times dy over y, right? And now we are actually at the point where we can think of integrating this guy, right? So this is called the separation principle, right? So you simply separate these two things and then you can solve it. So, okay, now we're going to do the integration. So if we integrate dt, it's going to be t. And if we integrate this guy, it's minus t. And 1 over y dy integrated is the logarithmic of y, right? Okay, and we got some integration constant. We're probably gonna stick this guy in here. Let's see, because when you do the derivative, you're losing some information, and we're gonna take this with us, right? Okay, so what next? What can we do? Actually, I'm gonna write this guy here. It's nicer. Plus c, doesn't matter. All the information which is lost, we're gonna plug in here. Then we're gonna divide by 1 over minus t. 1 over minus t. Then we come up with minus 1 over t times t. And then we have obviously something plus or minus, sorry, minus c over t, but we don't like to use that, right? We simply write plus c bar, and this is equal to the logarithm, the logarithmic of y. So what's the inverse function? If we want to get rid of the logarithmic function, we're going to write the exponential function, right? So if we want to have exponent of logarithmic y, this is equal y, right? Okay, but here on the other side, then we have minus 1 over t plus this constant here. Okay, so again, our constant shows up now at the exponent, which we don't like. Okay, we can write this e to the minus t times t, and this is basically plus, right? And this means e to the power of e to the power. So we can separate this in a form that we have e to the power of c is equal y. Okay, again, we don't like this guy, so we simply rewrite our constant, and now I'm running out of indices. Let's write c hat. Okay, so we come up with c hat e to the power of 1 over t times t is equal y of t. And this is obviously not very nice, because I fully forgot always the h. So this is the homogeneous solution, right? Okay, let's kind of right. So this is the homogeneous solution. Okay, so this is how your system reacts when you don't have an input. So what does that actually mean? I don't have an input. Well, I'm not exciting my system, but I still could have an initial condition there, right? And this is actually what stability is, right? I don't have to excite this, but I could have an initial condition. I let it go, it falls down, it's unstable. Okay, but everything you need to know about stability is actually found in that equation. So, what constraint do you need that this system is not going to infinity? Well, the exponent here, let's mark it. This guy here needs to be negative, right? So t is always going to be 0 or positive. So it really depends on our time constant. If our time constant is larger than 0, this exponential function will go to 0. However, if we would have a time constant bigger than 0, right, smaller than 0, right, this guy would get positive and our exponential function would run to infinity. And this is what we would call an unstable system. Okay, this was more like an aside. We will discuss that more later on. For now, we still need to solve for this guy here, right? The particulate solution. Okay, scroll down a bit. Okay, so particulate solution. Okay, so we know now that our input comes into play. And this guy simply is equal 1. So it's the unit step, right? So we simply write 1 because we don't care about times smaller than 0. Okay, and this is the so-called, what you can use here is the so-called approach of the right-hand side. It sounds fancy, but it's actually pretty simple. So what's your right-hand side here? What's this right-hand side? Well, it refers to the right-hand side of the ODE, right? So this is simply this guy here. Okay. And the approach of the right-hand side just means as our system is linear, our particular solution somehow needs to look like similar than this right-hand side. Okay, so our right-hand side is simply 1. It's a constant. Okay, we know it's a linear system, so our particular solution is also constant. We don't know what the constant is. We only know that it needs to be constant because this is the properties of a linear system. I guess you have learned this in your math lecture. If you would, for example, have something like u of t being 1 plus, let's say, t squared, then it's going to be yp is a0 plus a1 times t squared, something like that. But in controls, we actually have pretty simple inputs. That's what we discussed today. So it's actually always kind of like this, right? If you have a sine wave, you know your output also needs to look like a sine wave. For us, it means the approach of the right-hand side. This guy here is constant. That means our particulate solution needs to be constant. Okay, so if we have this, we can build the derivative. And this is simply 0. Okay, and now we're going to take that and insert it into our ODE. So all of this should be recaptured, right? Okay, if we do so, our ODE was t times y dot of t plus y equal kp times u. Okay, we plug that in. Then we have times 0 plus a0 kp, and this u was simply 1. Okay, so our a0 is going to be kp. And this results, our particulate solution is simply kp. Okay, so now we can fuse the two results. Because we know our y of t is equal the homogeneous solution plus the particulate solution, and now we have something like, I think I call it c hat e to the power of minus 1 over t times t, and then we have as particulate solution we have kp. So question to you, are we done yet? So could you now draw the graph of this y of t, because this, as an engineer, this is what you're ultimately interested in, or is there something missing? Maybe you can answer in the chat. Yes, so we cannot draw the graph yet because we don't know this c yet, right? So we need to go for initial conditions. So the initial conditions are missing yet. Okay, what can we say? Okay, we can say we are in equilibrium and we're going to make our life easier. At t equals 0, our output is 0. So our y of t equals 0 is 0. Okay, so we plug that in. Then we have 0 is c hat e to the power of, if we plug in a 0 here, it's e to the power of 0, which is basically 1. And we have plus kp, right? So what we get is that our c hat is nothing but kp, minus kp. Okay, now we are done. And the result is simply kp, and I'm excluding kp, and then we have 1 minus e to the power of t over t. Okay, so This is the result, right? What you would get. This is y of t for a step input. If you have a different step input, it will be a larger. As I told you, the input we had was, sorry, u equal 1. Now, if you would think of what happens u equals 3, because the system is linear, you could just simply say, take this by 3. Right? Okay, not doing this at this point. But this is a nice property why you can actually restrict yourself to these simple ones. Okay, what I want to do with you is a little bit of interpretation what we are seeing. So, if you want to now draw your graph y of t over t, we said, okay, we're going to start from here, and if we let t go to infinity, no, not 0, t go to infinity. Oh, it doesn't like me today. Okay, let's do it this way. Okay, maybe not. Okay, now it's working. Okay, so we let t go to infinity. What happens? Well, y of infinity is equal. So this guy here goes to 0. So what remains is kp, right? So we can say, okay, if we are just waiting long enough, then we're going to approach kp. Yeah. So remember, this is a little bit of kind of, it actually is kp times u, right? But u is equal 1. That's why we are approaching kp. Okay, but at the beginning, we are starting here, right? Okay, and in between there is this exponential function, this transition, right? And this is actually what this guy here is doing, the eigenmotion. Motion. This is what you actually see here in this area. Here you have this transfer behavior, which is composed due to the eigenmotion. So one nice thing is, you understood, I guess everyone understood a proportional system, right? We said a proportional system is nothing but taking the input and multiply it with a constant. And what you see here, that if you wait long enough, if you wait, your PT1 system, so a system with a first order lag behaves like a proportional system, right? So this lag basically vanishes at some point. It goes away. And then what remains is a proportional system. And this is true for every stable proportional system. If it's unstable, what would mean that this guy here would go to infinity, then it's obviously not the case, because then it would look like this. So you can wait very long time, it will not come to get to a steady state value. But again, this is a discussion for later. So this is, I think, a nice interpretation when you don't know what a PD1, a PD2 is. Just wait long enough, it will be a proportional system. But for us as engineers, obviously this eigenmotion is crucial. Think of your espresso machine. If this is a PD1 system and you need to wait 3 hours, so your water heats up, it's going to be not a good espresso machine, right? Or if you buy a car and you want to accelerate to 50 kilometers per second, and it takes 2 minutes, it's probably not a car you want to buy. So this is what the eigenmotion defines. For a PD1 system, this eigenmotion is only defined by this time constant. And I hope I could kind of explain to you what this time constant actually means and comes from with these electrical examples and with these hydraulic examples. Okay, so this is the solution to a PD1 system. I've shown it to you. As I said, you will never, in controls, you're never going to need to solve an ODE on paper in the time domain, but you need to understand what's happening, because this is the important point here. Really try to understand where is the connection between a physical system and these strange things we learned in our math lecture, right? And this is kind of, this system dynamics part in controls tries to relate these two things, right? As engineers, we like to have mathematical models of our system, of our aircraft, of our wind turbine, or of our car, and we need to solve that equation to know what the output is doing. We are ultimately only interested in the reaction of our system to a certain input. The PT1 system is one of the most basic systems, but this idea of having a lag, and you will always have a lag in reality, right? Even if you can approximate it with a proportional system, there will be some lag because you have structure dynamics, but it will be so small that we can simply neglect this, right? So engineers like approximating stuff. Okay. I know on the lecture slides, there's actually coming now on the next slide, there's this room example coming with this room with the temperature changing, but I decided yesterday to skip this because it's not very, it has actually 3 different inputs, and you can go over this at home and try to think what's happening. The story there is that you have your room, and you have different inputs, right? The output temperature can change, you can open the window, or you can change the heater, right? So it's still a PT1 system, it only has 3 inputs. But at this point, I think if I go over it, it's more confusing than helping. That's why I decided to skip that in the lecture. What I want to do next is a proportional system with a second order lag, right? You should know now, first order lag means we have the first derivative of the output, second order, we simply have the second one. And actually, this is the most important system, right? If you understand this, you have already covered a lot, because this is the, well, the PT1 is important, but I think the PT2 is even, especially for mechanical engineers, is even more important because it has the property that it is able to oscillate. And we will see this immediately. Okay, switch over. So, proportional system with a second order lag. Okay, I'm going to start out with the ODE first, right? Because, and actually I'm going to try to build it from behind. We again have this proportional part here, right? So our input is transferred proportionally to our output. Okay, let's write the output. Our output again is y of t. So it is second order. So now we have the first derivative and we have the second derivative there. And at this point, we will have a case discrimination, right, on this. This is why I'd like to only name this B2 and B1 at this point without actually discussing this at this point any further. They are not time, they don't have to be time constant at this point. They are just any parameters you have, right? Important here is it's second order because you have the second derivative there. Okay, so we are now made our life a little bit harder, right? We move from a first order system to a second order system. So if you remember what you learned probably in high school and in your last year and how to solve differential equations, and then hopefully in the math lecture here at the Hochschule, you will know that we can actually simplify, or we can solve this second order ODE with a nice approach with the so-called characteristic equation. So we don't and this is the only thing what we actually need to solve this ODE is the midnight formula. So I've also learned this midnight formula, or the name midnight formula in Germany. So I was not aware that this name actually exists. So the Mitternachtsformel in Austria, it's simply called equation to solve a second order polynomial. But if you know it as Mitternachtsformel, you should know what we are heading to now. Okay, so the analytical approach to solve this ODE is the so-called characteristic equation, right? So we take our ODE, and again, we are talking about the homogeneous solution, right? So please really, that means our input is 0. So we only take the left-hand side, and we replace all the derivatives here with simply lambda and the power of the derivative. So if you have the second derivative there, this exponent gets a square. The first derivative gets lambda to the power of 1, which is actually lambda, and here we don't have anything, right? So it's simply 1. And then an approach to solve this ODE is simply by solving this guy. This actually might, why the heck is this changed to a quadratic function? Well, we will see immediately, and actually has a nice relation also to the first order system, to a PT1. Okay, so I hope you all know now how to solve this guy here simply by the midnight formula, right? So this is this guy. I know there's a large one and a small one, and you can have simplified versions of it. I usually like to simply use this one. This is because it's always the same. Okay, so we can solve for these lambdas, right? So what we actually did, we came from an ODE and only solved a quadratic equation. Why this is possible, we will discuss that in a second. So, when you remember your time in high school, you probably remember when you solve the Mitternachtsformel, it can happen that the output gets complex, right? Or real, which we usually like because we don't like to work with complex numbers. But here in controls, we will actually work with these complex numbers a lot, so we better get used to it now. Because you have the square root of b1 squared minus 4b2, this guy here can get negative, right? This here. So if this guy is negative, we will end up with a complex lambdas, and if it's positive, we will have real lambdas. Okay, so far so good. That's why we're going to start with a case discrimination. And when you look in your mathematical formula, you exactly have you exactly have this discrimination in it. So I actually going to show you that that's actually true. So I have my mathematical formula, and on the last page, I think there is how you solve ODEs, right? And this, I mean, you don't have to read this, but all this tree here basically makes a case discrimination for a second order system. So you can look in and you will find exactly this. We are not going to go how you solve it. I will just show you the solutions, how you find it also in your formula. Okay, so the first case, we're going to say the square root is positive, then our lambda 1 and lambda 2 is real. So don't be scared, this is just a mathematical writing style. That means you get real values. So for example, lambda 1 is -1, lambda 2 is -5, right? Something like this. Okay, if they are both real, you know that your homogeneous solution looks like this. And now you should figure this looks pretty much similar to our first order system, which we just derived on paper. It's just two of these guys now, right? And this is one key finding of this whole differential equation theory, that we know that the homogeneous solution always has exponential functions. And this is why we actually can get rid of all integral solving and so on. We are simply solving this characteristic equation. And what we get out are the exponents of these exponential functions, right? You can actually also solve with this approach pretty simply a first order system. You don't need to do any integration. So probably this is an exercise at home, right? Simply try to do this. You will not end up with a Mitternachtsformula. Try to solve a first order system with via the characteristic equation, and not like we did just before by integrating the equation. It will be the same, but it's much simpler. Okay, so point is here, what you should see is that this looks similar. If these guys are real, so if lambda 1 and 2 are real, the homogeneous solution looks similar to the PD1 system. It only has two of these exponential functions. And the matter of fact is, so the secret here is, indeed, if you have a PD2 system, and your characteristic equation gives you two real eigenvalues. This is what they called. So these two real lambdas, then it's a PD2 system, but you can decompose this PD2 system in two PD1 systems. right? So nothing new here for us because we already know how to tackle a PT1 system. Okay, remember, you solve the characteristic equation, your lambdas are real, it just tells you now I have two PT1 systems. And this is why this case is not so interesting for control engineers or for engineers doing system dynamics. The other case where these guys get complex, right? So this means they are they are complex. For example, you could have, let's say, -1 plus -i, right? This would be the example. Then you somehow come up, the homogeneous solution has a cosine function in there. This exponential function only shows up once with the real part, so with this -1 here, and the complex part leads to an oscillation. Okay, again, please, you don't need to know how to solve a second order ODE in controls. But what you need to know is that if you have a second order system, it can oscillate or not. This is the key finding here, right? We're not gonna solve that in a second order ODE on paper. So you don't need your mathematical formula for the exam and so on. You don't need to solve this, but you need to understand if I have a second order system, it can oscillate or it cannot. It depends on the homogeneous solution, right? On these lambdas, on the Mitternachtsformula, last but not least. Okay, next we're gonna look at the time responses of the two cases, and we're gonna start with the more boring case with the non-oscillating case. Okay, so, and this is gonna go quick. So for a step input, and this is already the solution, right? So yeah, I'm just writing it there. For me, it's really important here to understand if you solve this ODE, the second order ODE for a step input. So remember now here, our input is again step input. This is your y of t. So what you see here again is you have this two exponential function. And by the way, this guy here is just C1, right? And so on. So this is a constant. It looks messy, but it's pretty just a single number. What's important here is these two guys. So they are both basically introducing a delay in your response, right? So let's do a very simple thing. Let's say what happens if t goes to infinity here? Well, and we assume lambda 1, lambda 2 smaller than 0, right? So if we let t go to infinity, this guy here will get to 0, and this guy will get to 0, and what remains is again a proportional system, right? The same thing as we had before, just wait long enough, it will act like a proportional system. However, this time we have two lagging contributions, right? We have this exponential function twice. So what it physically means is when we go back to this from this abstraction and think about a physical system, we have an input, we feed it through the first PT1 system, it's going to get delayed, and this delayed signal we're going to feed through another PT1 system, and it's again going to be lagged, right? So the output has more lag, depending on obviously on our lambdas, but this is the plain simple expression what a non-oscillating PT2 system is. It's just a row connection of PT1 system. It takes your input signal and lags it twice, right? This is what you see from here. Okay, and the remainder of this is actually just for you, if you want to dig deeper, to understand that you actually can rewrite a PT2 system, which is here, into two PT1 systems, right? And you can do the transformation, right? So what's important is that if this is the case, you just need to take the negative inverse of your lambda, and they're going to be your time constant of these two PT1 systems, right? Remember, a PT1 system has one time constant, two PT1 systems, each one has a time constant. So if you know that your system has real eigenvalues, you know it's just a composition of two PT1 systems, and the time constant of each PT1 system is just the negative inverse of this eigenvalue. Okay? Okay. Long talk. Now let's talk. Let's see how the step response looks like. Well, here is an example. I've chosen a PT2 system with a time constant of 0.5 seconds and another one of 1.5. Our gain is 2. Okay. So how does this guy look like? Actually, you could say it looks like a PT1 system. Well, I agree. The main difference here is, and this is the key finding for you here, that actually the slope, so the slope of your output at t equals 0 is 0. So any higher order system than a PT1 always has this property, right? Otherwise, I agree, it pretty much looks the same. So, however, you have some more delay, right? You have some more lag in the system than you would have in a PT1 system. And this is caused because of this guy here. You don't have a y dot at t equals 0. So the inclination of your answer is 0 at t equals 0. Remember, a PT1 started immediately. So there it had a y dot of 0 not equal 0. Okay, but let's write this down. We'll change the color. Okay, again, we said if we just wait long enough, we will converge to this our steady state value, and this steady state value is nothing but this Kp times our U0, right, for a step input. So if you want to do an experiment, and the matter of fact is you're going to do an experiment in lab exercise number 2 to compute this gain here, you just need to measure your y of t going to infinity, and in fact, in reality, you don't need to wait until infinity, right? Because this is going to be rather long. You just wait long enough, because you will see in the simulation that it fades out. And divide this by your input, right? Again, if you do a step input, this is always going to be 1, a unit step. But you could think of a different step input. For example, with espresso machine, we had 0.25. Then you need to take this into account, that the step input is not 1, right? Because it's linear scaling with this. Okay. As I said, a PT2 system has no initial gradient. So this is really important, because this is a key finding. Why is this so important? Why is this important? We said, okay, PT2 has no initial gradient. Well, think it the other way around. I give you a system like this espresso machine here, and I say, I will want you to, or your boss says, not me, right? Because your boss says, design a controller for it. And you have no clue how this system looks like mathematically with an ODE, right? So you're screwed. So what you can do is you take your piece of hardware and just put in a step, and it will react. And it might look like a PT1. I said, is this a PT1 system or is it a PT2 system? Well, you could look at this initial gradient and say, it doesn't have an initial gradient, it must be PT2. So it makes sense to approximate that system, what I have on my desk, with a PT2 system, right? So this is why you should always keep in mind how such systems look like. Okay. So I hope this is some motivation for it. So what means that your y dot at t equals 0 is equals 0. Okay, because of this, it has this nice S shape. So whenever you figure out an S shape, and let me try to explain what this S shape means. So I'm accelerating a little bit, right? So this looks like an S here, right? A PD1 would more look like, a PD1 would not look like an S. A PD1 would look like something like this, right? So you have a discontinuity in there. It's not a smooth S. So this S shape comes because of this high order delay. And what you also see, well, it's not that easy anymore to get your parameters out, right? You get a system of two equations, you do the experiment, and you figure, okay, I'm doing like a tangent here, right? This is the red one is the tangent. You measure that time delay, you measure that from the inflection point, this TW, and so on. So it needs a little bit of more effort to do an experiment and come up with the equation, but you still can do it, right? So, but you need to measure like four variables, and then solve for these two equations. Okay, so that's basically it for the non-oscillatory case. There's not much to say really. The important is a PT2 system with real eigenvalues is just a composition of two PT1 systems, and we already understand PT1, right? The other thing is, how do you realize what a PT2 system is when you do an experiment? Well, it's basically has this S shape, right? Okay. Thing is, in practical exercise number 2, or you might figure that out by yourself, what happens if you're not sure if it's an S shape or not? Well, then you say, is it either PT1 or PT2? And this is more like a practical tip, right, for you if you ever bump into that problem. If you are not sure if it's an S shape or not, then the second lag introduced by your second system is probably not important enough that it shows you an S form. So you can simply say, okay, it doesn't matter. I'm just saying it is you're approximating the thing by a PT1 system, right? Okay, let me try to convey what I mean. So if your system response has really a nice S shape, like this, right? You could say that's definitely an S shape, it must be a PT2. But if it has just a very small S shape like mine actually has here, you said, okay, this S shape is not very pronounced practically. And this would indicate that you can get a very good approximation of that system even with a PT1 system, because the second introduced lag of your second PT1 system is not important at all, because you barely see it in your time response. Okay, this was a practical tip. And the matter of fact is that you actually have that issue in the first lab exercise because it's actually already a PT2 system, but it looks like a PT1 because the lag introduced, the time constant of the second PT1 system is so fast that we actually hardly see it. Okay, now we've got 20 minutes left and we're going to start with the oscillating system, with the oscillating PT2 system. Remember, oscillating means you compute the eigenvalues, you solve the midnight formula, and the outcome, the square root is negative, the outcome is complex. You immediately know your homogeneous solution has some cosine function in there. And you know, a cosine function always kind of leads to oscillation. And if you remember back, I think it's TM2 or TM3 where you do dynamics, and this is what you should have covered already. It's only in the context now of system dynamics and not dynamics anymore. A spring mass damper system for a mechanical engineer which is oscillating is probably the most basic example for a second order oscillating system, right? I mean, if you turn up the damper, you increase the damping, at some point it will not oscillate anymore. Then you end up with a PT2 system which is non-oscillating, which has two real eigenvalues. Okay, so let's go over and discuss again this oscillating case. So we said oscillating means we have the solution of our characteristic equation, which comes from the midnight formula. They are complex. Okay, so let's write down the this guy one more time. Plus b1 times y of t plus y of t is equal kp times u of t. Okay, And now we're going to redefine this, and this should somehow look kind of familiar to you. So if we know if lambda 1 and 2 are complex, right? Then we will rewrite, and we're not going to use B1 and B2 because we don't like this, because they don't tell us very much. We're going to write, instead of B2, we're going to write the negative inverse of the eigenfrequency squared. And instead of B1, we're going to write 2 times a damping coefficient over omega 0. Okay, so let's do this. We get 1 over omega 0 squared times y2 dot of t plus 2d over omega 0 times b of t plus y of t is equal kp times u of t. So this is really a formula you should have seen before in technical mechanics. It's a second order system, and it has some damping, it has an eigenfrequency, and yeah, it basically has Kp. So instead of sorry, instead of using the proportional gain, well, we use the proportional gain Kp. We know what this is, right? But instead of using these strange parameters B1 and B2, we as engineers rather use a damping and the eigenfrequency. Why? Because these parameters tell us something, right? If I tell you it has a damping of 0.7, you probably know it's going to oscillate. If it has a frequency of 10 Hertz, you probably know, oh, it's fast or it's slow. But if I tell you B2 is equal 100, you have no clue what it is. So instead of writing with some random parameters B1 and B2, we introduce now the eigenfrequency and the damping, and we easily can calculate those from this B1 and B2. So this is the idea. Okay, one side note, because we'll need to use that also, is you can rewrite this equation, obviously, right? You can say y2 dot of t is, sorry, not is, plus 2d times omega 0 y dot of t plus y oh my God, y of t is equal y0 squared times kp u of t, right? So you can also have this form, and we will make use of this. Is just multiplying this guy here by omega 0 squared, right? It's really just the same. I know it's simple at this point, but it's often gonna get confused here by students, and simply why. If I give you a second order ODE, it will have numerical values, right? It will have 10 times y2 dot and so on. And then I say, okay, please compute the damping and the eigenfrequency, right? So here it looks simple, but then you need to transfer it over to like numerical values. And the important here is really the only problem you can fall over is that you need to make sure that here you need to have a 1, or here you need to have a 1, right? And then you can do a comparison of the coefficients, so ein Koeffizientenvergleich. If you don't have that, it's going to get messy, right? So please keep that in mind. Okay, so if you solve that equation for a step input, it looks like this. Again, step input, right? 1. Okay, this looks pretty messy. I fully agree. But what can we read there? Okay, what we read is, for sure, our output has a sinusoidal wave in there, right? So it's oscillating. But it also has an exponential function in there. And if d are positive and omega 0 is positive, this function is going to decay. So we can definitely say what can we say about y of t? Okay, let's say what happens at t equals 0. Well, if d is equals 0, then we are left with the initial conditions, which are 0. The more important thing is what happens if t goes to infinity again. Well, if t goes to infinity and we assume d and omega are bigger than 0, well, what remains is y of t is equal kp, right? So again, also for this system, we are sure that our system behaves like a proportional system if we just wait long enough. Okay, so if you want to draw that, we will converge to kp times u0. u0 here is 1, so we converge to kp. And in between there's some oscillation, right? Okay, if it's oscillating, it might look like this, right? Okay. That's all we can say here, and this is actually what's important here. So let's define these parameters. This omega 0 is basically your natural frequency of your undamped oscillation, right? D is the damping, like we've learned in mechanics. And if you want to take a closer look at this term here, this is the so-called frequency of the damped oscillation, right? In reality, this oscillation here will fade out if the system is stable, and you can compute the oscillation by just looking at the period here. I think that's on the next slide. Okay, so our system now is, again, not characterized by some time constants. If the system is oscillating, we prefer talking about the natural, about the eigenfrequency and the damping. And obviously, again, of our proportional gain. Okay, so this is the solution if you would solve it, but we are more interested how the plot looks like. Okay, so next what we're going to do is we don't going to look at a single plot. The characteristics are the same as for the non-oscillatory case. The main difference is here the eigenmotion is able to oscillate, right? If you wait long enough, it's still going to converge to a proportional system-like behavior. It's still going to have this S shape at the beginning. So the only difference here is really what happens in between the oscillation. And here we're going to take a look at on our omega 0, on our eigenfrequency, and on our damping. How are these parameters influencing this eigenbehavior, right? So we basically moved away from eigenvalues which are complex and barely tell us anything if we look at them, to rewriting the equation to real values, the eigenfrequency and the damping. And now let's see what happens to a step response when we change these two values. Okay, so sorry, got lost. Okay, so this is a PT2 system where I simply kept constant the damping, and I just changed the frequency. So when we increase this frequency here, so this means the omega 0 gets bigger, right? What you see here, the system gets faster, right? And this is called the so-called settling time, right? The overshoot is somehow how much do we overshoot our final response, and this overshoot is not changed. Okay, I'm going to define these two things later. I'm going to try to get some intuition on the system. Okay, so increasing the natural frequency means faster response, and we're going to mathematically describe this by the settling time. Okay, how can you remember the settling time? In German it is Einschwingzeit. That means how fast do we actually get to our final value? How fast do we get, how much time do we need to actually converge to a proportional system-like behavior? And obviously you should see the green one is much faster than the orange one. So, okay. The overshoot, this is quite interesting, especially for flight mechanics, means how much overshoot do we have? So really, how much do we overshoot our final value at the beginning? How much overshoot does PT1 system have? 0. It cannot oscillate, it cannot overshoot our final response. So overshoot is only valid for oscillating systems. Why is this so important? If you design control systems for an aircraft and the pilot pulls the sticks and the system is doing, and he wants to go here with the nose and it's going to do like this, there's too much overshoot. So this is an important parameter to evaluate your system. Okay, so overshoot does not change with our frequency. Okay, this is a finding. Okay, now let's talk about what happens if we change the damping. This should be kind of clear from a PT2 system in mechanics. If I decrease the damping, it's going to oscillate, and it's going to oscillate a lot, and it's going to overshoot a lot, right? So if this example here has 3 radians, so it's basically it's basically the green one, and for this green one I change the damping, and if you make the damping smaller, it's going to overshoot, right? Although, I mean, it changes a little bit the settling time, but not much. Okay, so decreasing the damping leads to higher overshoots. That's what you see here. And for the stable oscillatory system, well, the speed is not changing with the damping. Okay, so this is, yeah. So we have some additional 2 parameters. We said, okay, damping and frequency are important, but why are they important? Because they are related to speed in our system and oscillation. How much is this oscillation, right? So instead of talking about eigenfrequency and damping, we can also talk about settling time and overshoot. And settling time and overshoot are basically defined by the combination of these 2 parameters. So now we need to define these 2 parameters. So I hope, Oli, I get healthy over Easter. Okay, next page. Let's talk about this overshoot. Actually, it's pretty straightforward to define the overshoot. The overshoot just means how much do I overshoot over my steady state value, right? So let's define this. The steady state value is here, right? It's simply A0. So for a stable system, this would be Kp times U0 if you do a step response, right? Okay, and the overshoot is basically, you only need to take a look at the first peak here. How much do we overshoot here? Okay, so now we can define, okay, this overshoot delta H, that's just the name of the overshoot. We say, okay, let's take the maximum of our y of t, the maximum regarding to t, right? In this plot, this would be 0. You still need to only look at the first one, because for a stable system, all the other peaks will get smaller. Okay, and then we're going to subtract the steady state value, which is nothing but we wait a very long time, or just long enough until it's constant, right? So this is this A0 here. And then we still need to, if we want to have it in percentage, because overshoot is often referred in percentage, we simply divide this by this final value. Okay, so if you want to have percentage or not, depends on you. If you want to have it, you can multiply it by 100, and then you will get the whole thing in percentage. Okay, so if you look at this figure, the whole thing is actually pretty, gets pretty easy, right? So what's this here? This is simply this A1, right? So I take this whole thing and subtract the steady state value, right? And what remains is this A1. So you don't actually need to compute this guy here. You just need to take a ruler and measure out this one. And then you divide it by A0 and multiply it by 100. That way you could determine experimentally the overshoot. You can also compute it, but this is a little bit more involved. I think in lab exercise number 2, we were going to do this once. And by there you will see that it takes a very good eyes. Because you can also compute it with this A1 and A2. The problem is that when the system is pretty much damped, this A2, you will not see this A2 anymore and you will need to zoom in. But technically you can compute the damping of your system by this A1 and A2, right? So, and also your frequency. Okay, why is this important here? Well, again, you don't have a clue what B1, B2 in your ODE is, or what your eigenfrequency is, or what your damping is. You only do an experiment, like we do with the espresso machine, and then you want to get back to this ODE. And with these formulas here, you actually could do this. You could, if you know, for example, the overshoot, you can compute A1, or you can directly measure A1. And with A2, you can track back to your ODE. Why is this important? Because you need the ODE to design a controller later. Yeah, I see you next week. Stay safe, stay healthy, and bye-bye.